acerca del Dr. Cornelius Masuku. Okay? Dr. Cornelius Masuku is an associate professor of engineering practice in the Davidson School of Chemical Engineering at Purdue University. Now, he was previously a postdoctoral researcher in Lawrence T. Beigler's group at Carnegie Mellon University. He holds undergraduate degrees in chemical engineering and computer science and a PhD in chemical engineering from the University of Witwatersrand in South Africa. Now, his PhD thesis was on the interaction between reaction and phase equilibria in the Fischer-Tropsch reaction and was advised by Professor Diane Hildebrand and Professor David Glasser. He tested catalyst and developed reactor models that performed part of the design and commissioning and startup of a coal to liquids pilot plant in Baoji, China. He spent a year at the University of Kentucky working on catalyst development, characterization, and testing on slurry phase reactors with Professor Burton H. Davis. Now, also, Dr. Masuku received a faculty position in 2012 at the University of South Africa, where he taught process control and reactor technology to seniors and advised one PhD and 6 master students to completion. He was tenured and promoted to associate professor at the end of 2015. He, thereafter, spent a year at Texas A&M Energy Institute under the mentorship of the Professor Christoph Dolos A. Flodas, working on hybrid energy systems. He transferred at the Carnegie Mellon University, where he co-advised 7 master students to completion with the Professor Beigler. His current research focuses on algorithmic developments, conceptual designs, and optimization of biomass, coal, and or natural shale gas conversions to fuels, chemicals, and electricity, mainly through the Fischer-Tropsch synthesis.
So Cornelius, if you want to start, you are welcome.
Thank you so much for the kind introduction. I'll start sharing my screen. Can you confirm that you can see my PowerPoint slides?
Yeah, we can see it.
Yes.
All right. Thank you very much. Yeah, I'm very grateful to be invited to give this seminar here. So I thought I'll start with a brief background of the work that I've done, and also then bring into the mathematical programming for systems engineering, design, and optimization. Because yeah, when I got the invitation, the focus was more on the mathematics and its application to the research that I'm doing. And I understand that the audience is from different engineering schools. So I'll try to give like a broad perspective of the mathematical programming so that everyone can understand the concepts that are applied. And then towards the end, I'll give like an example which is more geared towards chemical engineering. But I think the whole seminar should be accessible to everyone who is in engineering. And the reason I decided to go with mathematical programming, I know mathematics itself is a very broad field, and a lot of it is used in engineering. And recently there's been a slight shift towards like a mathematical programming, which tries to find an optimal solution to a mathematical program. So I thought I'll give that. And thank you so much for giving a background in terms of my work. I wanted to use that background to motivate the work that I'm doing as well. So as they've introduced, my name is Cornelius Masuku. So I'm an associate professor here at Purdue University. So in terms of my work, so I completed my PhD in South Africa in 2012. I'm originally from South Africa. So I grew up in South Africa, studied there all the way from all the school years, 12 years, and also in college, undergrad, even PhD. So I completed my PhD in South Africa. And my research work, so I wanted to give you like a personal research story and then put in the how the mathematical programming comes into it and how I ended up here at Purdue University. So I started doing my PhD. I did a lot of experimental work, mainly consisting of modeling and experiments, all the way from preparation of catalysts, characterization, and testing it. So I worked with different types of reactors. I worked with fixed bed reactors. I worked with CSTR, slurries, and different types. And one of the advantages of working with some of the top researchers in South Africa is that some of the professors work with industrial collaborators. And I was lucky enough to be part of a team that worked on an industrial project. And we were tasked to come up with a design, optimize it, and build a pilot plant, which we did that in China. So the synthesis was based on the attainable region theory. The attainable region is also like a mathematical graphical technique where you try to find a graphical space of where the solutions could occur. So that's like the attainable region. So for any system, there are some things that you can achieve with that systems. So attainable region give you the space that you can achieve with whatever system that you have. So we use that type of mathematical process systems approach for this plant. And for me, I was involved at every part of the process, all the way from the conceptual, the experimental, and even the production of the synthetic crude. So this was one of the best learning of my life. So this is where I got a chance to see maths being turned from just numbers to actual plant to actual product. And one other thing, while I was towards the end of my PhD, I got a chance to spend a year at the University of Kentucky working with Professor Bertrand Davis. So there, since in South Africa, I worked more with fixed bed reactors and CSTRs. At the University of Kentucky, I got a chance to work with slurry reactors, which are just the different types of reactors, because I wanted to test some of the models that I had developed there in slurry reactors. And I also had a chance to work on some few Department of Energy research. And this somehow, in a way, brought up that curiosity. I saw the scale at which research is being done in the US and the pace at which things happen here. I was like, wow, I really like this place. I would like to come here at some point. And then when I went back to South Africa, I've worked on a lot of other processes. And but the main key that I'm trying to highlight here is that you can apply mathematical programming to a lot of variety of fields, a lot of application area. I mean, whatever you're trying to do as an engineer, whatever you're trying to build, you have to be able to describe what you're doing in terms of equations. And then once you have the description of those equations, you still have to try to solve those equations to find the numbers that go into your system. So I was involved in trying to develop like a small scale Fischer-Tropsch technology. So we decided to build like a 40-foot container where the whole plant will fit in there. We even showcased this at the COP17, the Congress of the Party, which is like the climate change type of organization that was in South Africa. And immediately after completing my PhD, I got a faculty position in South Africa. So I started working there. So I taught process control and reactor technologies has been introduced. And I also started advising graduate students. And from there, that's when I started broadening my research areas, because I had focused more in terms of producing fuels up to that point. But then I started focusing more on producing other chemicals and also producing electricity, because the process that I look at, mainly from natural gas, you can burn it to produce heat, which you can use the heat to turn the turbine and produce electricity that way. Of which, yeah, that's one of the things that I started looking at. And then, yeah, when I was at University of South Africa, after getting tenure, they had a very nice program where like young faculty can take 3 years and go anywhere in the world and they focus on research, and the university would hire someone to teach their courses. So for me, I decided I wanted to go work with Professor Fluders. And Professor Fluders had just moved to Texas A&M, and he was building his energy institute there. So I wanted to go there. And one of the main reason that I wanted to get into this program was to try to distinguish myself from my PhD advisors, because up to that point, most of the stuff that I had done, my PhD advisors had also done. So I wanted to do something beyond that, which my PhD advisors have done, so that if there's anyone who wants to come to our university, wants to consult, at least maybe they'll have reason to talk to me rather than talk to my PhD advisors. So then at that point, I knew that I had a lot of like programming skills, so I wanted to go deeper in terms of computational programming. But then also wanted to expand my mathematical and computational part and fuse them together. Of which that's what attracted me to work with Professor Fluders, because he was strongly into the mathematical programming and computational algorithmic development. In fact, he had developed like a few solvers. Some of the few commercial solvers that are out there, some of them have been developed by Professor Fluders. And I mean, yeah, Professor Fluders did his PhD at Carnegie Mellon. So, and a lot of the top solvers are actually coming out of PhDs from Carnegie Mellon. So yes, I spent some time there. So I started working on mixed integer nonlinear programming and deterministic global optimization. So the whole point when I was there, the focus was more in terms of the multi-scale systems engineering. So Professor Fluders was starting to work with like biomass, gas, and coal, and I already have been working with those type of systems. But he knew more in terms of the maths and the algorithm, and I was bringing more in terms of the concept. So then there was a mutual experience there. So then that's what attracted me there. So with deterministic optimization, you set up your algorithm and you're trying to find the best possible, mainly for optimization, you're trying to either minimize or maximize. But mainly in our field, we look at trying to minimize. So even if you have to maximize a certain function, you just take the negative of that function and minimize it, so that you can solve everything as a minimization. So yes, but feel free to stop me and ask questions if you have questions in the middle. But okay, I think maybe that's something else. But yes, so there's a few algorithms that people use, like your branch and bound, and you usually formulate your problem and it's dual, and you solve those to find the upper bound and the lower bound. So I spent some time at Texas A&M, but then Professor Fluders passed away when I was there. So then I decided to transfer to Carnegie Mellon University and to try to continue in that area. And when I was there, I focused more in terms of the nonlinear programming. And nonlinear programming is like a subset of the global optimization, where global optimization, you're trying to find the ultimate minima. Meanwhile, nonlinear programming focus on like a local minima. For whatever systems that you have, you try to find a minimum point for that system. But then there are ways of formulating problems to be like nonlinear programs and still try to find the minimum point for that. And there's a lot of like, because you have to provide an initial point for whatever system you're formulating, and then there's ways to find the solution to that. So when I was at Carnegie Mellon, focus on designing like reactive distillation system. Yeah, I think that makes sense to mainly chemical engineers. But then when I was at Carnegie Mellon, then I was getting very good results. And then I wanted to extend the program that I was on because at the end of the 3 years, I was supposed to go back to South Africa. So I tried to talk to my university to give me a few, like an extra year or something like that. So they refused. So then I decided to leave my job. So I resigned from the University of South Africa and started applying for faculty position in the US. And I got the faculty position here at Purdue University. And now here at Purdue, I'm working on a number of research projects. I'm also still building my research group. Now I currently have one PhD student that I'm advising, but I'm planning to get more, maybe another one in the fall, but also grow my research group that way. So I'm working on developing like modular gas to liquid processes, and also coming up with intensified design. So we look at membrane reactors as well, and we're also looking at integrated product refining. But the key there is coming up with algorithms to try to, because some of these processes have been known for quite a while. And the main problem is that once you can write the description or the equations that describe that process, trying to find a solution to that is a bit challenging. So that's what I try to focus on, as to what algorithmic improvement can you come up with to be able to get to the solution that you want within a given reasonable period. So that's one of the things. And besides that, I'm also looking at like innovative combination of processes for alkane utilization, because the US has a lot of shale gas, and with shale gas, it also comes up with some of the short chain hydrocarbons. And the alkanes are not so easy to convert. The alkenes can be easily converted, but the alkanes are not. So we're looking at ways and means to convert those. And also coming up with like reduce order models for other systems. And in terms of the actual application, there's quite a number of application areas that I'm looking at, and hybrid energy systems modeling is one of them. And I think this is more relevant for, because most engineers need to work together to produce like an hybrid energy system. If you want to produce electricity or make use of the mechanical work somewhere, so you need to have a multidisciplinary teams, and understanding the math, the mathematics that describe the process, and then coming up with solution is actually key here. So I think these are some of the examples that maybe might apply to everyone who's attending this seminar. But yeah, and one of the big motivation for mathematical programming, in a way, I think the pandemic has made a lot of things pretty obvious, that we do need to have a way of being able to work remotely. So what is happening in industry now, a lot of companies are installing like real-time optimization system to be able to run their plant and change parameters like remotely. And with that, we are also trying to develop optimization system to try to find optimal point for the systems that you can implement on the plant so that it can run by itself. So that's one of the things that I'm actually looking at. And for me, this is more motivation that I think more engineering students should try to go deeper and trying to understand more in terms of mathematical programming or coming up with algorithms to make things run faster and run better. And in terms of the scope and the application and the opportunities, they are huge. So now, yes, coming to the actual core of the math that is behind, I wanted to get to the actual key of the talk. I don't know if there's a question for anything that I've just said before, or should I just continue and get on the math?
Dr. Cornelius, this is Daniel Velez. We cannot see your slides changing, so I don't know if this is correct or you maybe are sharing a different screen. Just checking.
Oh, you cannot see my slides change.
We can see the slides, but they're not changing. We just see the screen that it was in the beginning.
Oh, you only, oh, wow. Yeah, I've been changing my slides. Okay.
Yeah, sorry, and I didn't want to interrupt you, so, but I just took this chance.
Oh.
Maybe you just need to put in mode, presentation mode or slides mode.
Oh. Let's see.
There you go.
Oh,
Yeah, now we can see it.
You can see this, and can you see that it has changed now?
Yes, yes.
Oh, wow. Oh,
sorry for
okay.
not telling you before. I just didn't want to interrupt you.
Okay, sorry about that. Well, yeah, hopefully.
Don't worry, don't worry.
Yeah, all right. So hopefully now this will be smoother. Besides that, were there any other question, or should I just continue now? Okay, I guess I'll just keep on going. So the mathematical optimization. So for the optimization problems, it's slightly different from like your algebra or calculus that most of you have been exposed to for most of the time when you were studying math. So with the mathematical programming, you're trying to formulate a problem that has an objective function. So you're trying to minimize the objective function, and in this case, that's f0 of x, and you have some constraints that you have. So those are like functions fi of x, and those could be less than or equals to bi. So there's a reason that you put them to be less than or equals to. But you can even formulate this as some equality constraint and inequality constraints, but that will still work here. So the main difference is that for an optimization problem, you tend to have some degrees of freedom. So your x, which are your optimization variables, you can have like an n number of x, which can be x1 to xn. But then your constraints, they need to be slightly less than the total number of variables that you have, so that you have some degrees of freedom to optimize over. So that's why you have your constraints here going from 1 to m instead of 1 to n. And then what you are actually looking for here, you're looking for like an optimal point or like a solution, which is normally denoted as x star, that has the smallest value of f0, that amongst all the vectors that satisfies the constraint. So what is happening is here is that you have a system that you're working on. It could be whatever system it is. I've shown some few examples. Well, yeah, you didn't see them, but okay, that was disappointing. But you could have a system that you're trying to work on. It could be trying to produce whatever, a power system or electricity production system. So you describe it with all the mathematical equations that you have. And then with that, maybe you're trying to minimize the installed cost or capital cost. So you set that as your objective function. And then the constraints are all the equations that satisfy, could be like the capacity constraints that you have on your systems. It could be the flows. It could be anything that describes that. So those will be the functions that you have as your constraint. So, and then you have your variables that are like x. So what you're trying to do, you're trying to find the value of x that minimizes the objective function. So that's the main key with that. And one of the most popular or the most successful form of mathematical programming or mathematical optimization that is out there is linear programming. This one actually was known for quite a while and was applied pretty widely, and it's very successful. There's solvers that can solve linear programmings with hundreds of thousands of variables. So you can have like 100,000 equations and give it to a computer, it will solve it and give you a solution. So here, the main thing with linear programming is that your objective function is a linear function. So, and all your equations are described by maybe ax instead of ax squared or something like that. So all the variables are linear or constants. And all your constraints are also linear constraints. So you have ax less than or equals to bi. And you still need to have the degrees of freedom. So you still need to have the the number of equations that you have to be less than the number of variables that you have so that you can optimize over certain variables. So this is one of the most successful optimization that is out there. And it's also one of the most widely applied optimization program that is out there. And I know that there are some schools that actually do offer linear programming as a course, of which I think it's very good because there's a lot of algorithmic power that you can use. And I know some people might think that, oh, linear programming, a lot of systems are non-linear. But the key with linear programming is that there's a lot of systems that are actually non-linear, but then you can linearize it to make your equations linear and solve it as a linear program. So this is one of the most powerful optimization tool that is out there and it's actually being used. And one of the big examples is that when you're trying to book a flight, wherever you try to book a flight, try to find a matching destination with a price, the algorithm that they use there is actually linear programming. I think they're using IBM's solutions to that. And I mean, now there's millions of flights. Well, I mean, there's millions of people trying to find flights at a particular time. And IBM has solutions that can easily solve that within like instantaneous. And in the past, people have focused too much in terms of linear programming versus non-linear programming, of which that was like the original main focus at some point. But then recently, people have actually noticed that in the past, people have always thought that, oh, the easy problems to solve are the linear programs, the not so easy problems are the nonlinear programs. But then of the nonlinear programs, there's also some programs that are actually easy to solve. Those are like convex problems. So then nowadays, there's also a shift towards like convex optimization versus non-convex optimization. So the convex part is that you still have your general optimization problem. As we've said before, you have your objective function and some constraints as well. But then the key point is that the objective function and all the constraints are all convex functions. So a convex function, it has to satisfy this criteria. This just means that it only curves up. It has a non-negative curvature. So that means if you have to take a combination of any point between alpha and beta that is on the graph, so the combination of the two has to be less than the sum of the combination of those points. So the graph itself is always just pointing out upwards. And then for convex optimization, you need to have all your functions to be convex and all the constraints to also be convex. And there's algorithms that can solve this type of problems and they work very well. They get you the actual solution that you want and they work within a reasonable amount of time. Well, yeah, alpha and beta have to be positive and the sum of them has to be equal to 1. That's like a convex combination of the two. And yeah, so I was contrasting linear programming versus nonlinear program. And nonlinear programming, I mean, there's still a lot of people that are working on nonlinear programs as a group of problems that they're trying to solve. So you're still trying to solve like a general optimization formulation. You have your objective and your and your constraints. So the main point is that all the functions have to be nonlinear, but you can have nonlinear and some combination of linear. But therefore, because once you have anything that is nonlinear, so it's no longer a linear program, even if other functions are linear. So you have a nonlinear programming. And the recent approach for nonlinear programming is that you're working with all the variables to be continuous. This means that you don't have any variables that is like a binary variable or like a yes, no type of variable, or an integer variable, like maybe 1, 2, 3, or something like that. So you need something to be continuous. So all your variables are continuous. And for most of the solvers that are out there for nonlinear programming, they need your functions to be smooth and twice continuously differentiable. The reason for this is because they tend to rely on the gradient of your function. They take derivative of your function to try to find the minima. So then they need to be able to differentiate your function. And in fact, the important part about nonlinear programming versus maybe deterministic global optimization or any global optimization algorithm is that they use like local optimum methods. You find the best point in the neighborhood of the points that you are. So for nonlinear programming, you need to give it like a starting point, and then once you have a starting point, and then you try to find the best point in the neighborhood of that point. And so then now we can contrast it with the global optimization. For global optimization is that for whatever system that you set up, you try to find the actual solution, the best case, the minimum for whatever you have. So you aim to find a global solution. And your equations could be linear, nonlinear, convex, or non-convex. So you try to find a solution for whatever you have. And the main challenge with this one is that it's really difficult to solve. So if for some of you that are interested in like complexities of algorithm, the worst case complexity grows exponentially with problem size. So if you have a problem maybe with like 10 variables and it takes 10 seconds, if you increase the number of variables, the complexity grows exponentially with that. And most of the algorithm for like your global optimization solvers, they're based on the nonlinear programming as sub solvers, or even linear programs sometimes as the sub problems that are used today. And then you need to have a method of breaking down the problem to few nonlinear programs and then keeping track of the solutions that you have for all the sub problems that you have, so that you can get the global minima. And then now in terms of the actual algorithm, is that this as a science is actually a little bit old now. I mean, the simplest algorithm has been known for quite a while. I mean, yeah, there's a paper that was published by Josh Danzig from Stanford in 1947. But even before that, I mean, the people in Moscow or in Russia have been doing research on linear programming even before Josh Danzig. So the algorithms have been known even before then. So the linear programming is successful because, yes, it's been known for quite a while. But somehow I think the penetration in terms of the curricula for engineering has been a bit slow. I think we need to try to bring this into our curriculum more, so that more people can learn more about these type of algorithms. And so around the 1960s, people started coming with interior point type of methods. So the early interior point method were somewhere around like the 1960s. So this method, if you know some of the solvers, you know that there's one solver that's, yeah, we use a lot at Carnegie Mellon, which is called IP-opt. It's based on like interior point methods. So these are one of the few like efficient algorithms that people have come up with to try to solve optimization problems. So they started coming up around the 1960s. And then somewhere around the 1970s, you have people that started to come up with like some ellipsoid method and other subgradient method. Most of the these two, the interior point method and the ellipsoid method, they work more. They applied more in terms of the nonlinear programs. And most of the nonlinear programs, they are subgradient method. A subgradient method is a method that rely on the gradient or the derivative of the functions that you're trying to solve. This is, in fact, this goes all the way back to Isaac Newton. I mean, he was the first one. I mean, in calculus, I mean, there's few things that you can solve. You can try to find the derivative of something to find the minimum. So most of these algorithms also rely on that type of concept. And then somewhere around the 1980s, people started coming up with like polynomial time methods of interior methods for linear program. So the early interior point methods were very good, but in terms of the time it would take to solve them, they were not so efficient. So around the 1980s, they started getting like very, very good. So nowadays, I mean, they are so efficient. We use them quite often. And then in the late 1980s, all the way to now, there's a lot of polynomial time interior point methods for even nonlinear convex optimization. I mean, yeah, for convex optimization, there's now a lot of efficient programs that people are using out there, and they're very efficient. And the main thing of which my point is that before like 1990, you had like very few applications in engineering of mathematical programming. In fact, a lot of the schools didn't even teach mathematical programming, even though linear programming was so successful even before then, but a lot of engineering schools didn't teach it. And you had a lot of applications in operations research. And even now, that's why operations research is somehow, most schools do teach like linear programming, and they apply it a lot in terms of planning and scheduling. It's mainly linear programming, and it's still applied now. But then since the 1990s, a lot of the other engineering schools is getting into the research, and then moving from research to the actual curriculum. There's been a lot of movement in that front. So there's also, in terms of the research, the people were starting to see that, oh, mathematical programming can be applied in a lot of areas. Could be like your control, your communications, process synthesis, or heat exchanger networks. So there was a lot of new application areas, and now mathematical programming is actually applied in a lot of ways. So yeah, I wanted to go to an example, but I wanted to pause and see if there's any question on anything that I've said at the moment, that there's some clarity that maybe somebody might want to have.
Chicos, ¿alguna pregunta que deseen compartir con el doctor Cornelius? Is there so many questions?
Oh, say somebody.
Adelante, Marco. Adelante.
I have a question. As an industrial engineering, that's what I'm studying.
Yeah.
How may I apply this to my field?
Oh. Yes, in industrial engineering, there's actually a lot of application. Mainly what I've seen from industrial engineering is like planning and scheduling. So if you have a system where you need to set up like your task and your operations. So in fact, this fits in well with the operations research. That's what I've seen industrial engineers and operations research working together, is in planning and scheduling. The planning, you have a task that needs to happen at a particular time, and you have, say, a sequence of tasks. So you can formulate that as an optimization problem, trying to minimize a certain cost. Most of the time is to try to minimize a certain cost or minimize a certain budget. So there's actually a lot of application in industrial engineering, mainly in planning and scheduling part.
Okay, thank you.
Thanks. Are there any other question at the moment? Okay, in that case, I'll also take a step and give an example from some of the work that I've been doing, just to give you a hint of how do you go about solving these. And also, there's also like a few other ways and means to try to solve systems this way. So I'm looking at modular integrated processes. So I mean, I'm looking at like shale gas processes. You're trying to convert your gas to liquids. You're trying to produce like your petrochemical type of fuels, like your diesel and gasoline and jet fuels. And one of the systems that I came up with is reactive distillation, which you could use to combine the reaction section and the separation part, which is the distillation section of your plant, to try to make your plant a smaller one. So, but the problem with this is that once you try to write the equations for this, the description of the process is very complex, and then trying to solve that is a bit challenging. So for the gas to liquids type of process, you tend to have like three parts. Mainly, you have your feed that is coming in, that you need to process it to mainly produce your CO and hydrogen, which is what you use in your reaction section to produce the hydrocarbons or the products that you want. And then after you have the products, then you have to separate them to get the right specification product that you want. So there's usually different part. For this seminar, I'm just gonna focus on part one, on just the steam methane reformer. So if you look at the steam methane reforming, there are some reactions that are happening there. So here I'm giving you just three examples on the reforming. You have your methane reacting with steam to produce CO and hydrogen. And but sometimes you can also find some of the CO that reacts with some of the steam to produce CO2, of which that's like a water gas shift reaction that also happens there. That's why all the steam reformers are not 100% efficient, because they do produce some CO2. And not just only that, also your methane as well can also react with water to produce some CO2. So then the efficiency drops there. And what you tend to use for the steam reformer is that the steam reformer happens at the high temperature. So you need to get to that high temperature. And one way of doing that is to burn some of your methane. So if you take methane and you burn it in oxygen, you produce even more CO2. But the good thing with that is that it releases the heat, of which is the heat that you need to heat your reactor to give the temperature that you want for the reactions that you want to happen. And then the main challenge with trying to describe this is that when you have to write down the equations that you use from the kinetics, they tend to be, they are clearly nonlinear. In fact, you have p to the power 3 there, so you even have cubic equations. Some of them have p to the power 4, of which, so the equations that you have are clearly nonlinear and clearly non-convex. So then to try to solve these, it's not just only a nonlinear program, because you might be stuck in a lot of suboptima, like not global optima that you want. So you might be stuck at the local minima. And so then the oxidation reaction also happens. So as you tend to have this reaction in a tube, you tend to have concentration gradients. So there's a change in concentration with the length of your reactor. So if you have to try to write out that equation, now you end up with some differential equation within a system. So now it's not just only like an algebraic type of equations that you have to solve. So you have algebraic equation and also have like differential equations. So you have like the differential algebraic equations. So the one thing that people tend to do, like currently, let's say if you don't know much about optimization, you can just try to formulate that problem and just solve it as a mathematical equation. So just to try solve that. So you can do that. So Python has very good packages. So I mean, I'm just trying to show you that here, if you use SciPy and use the Ranch-Kadam 45 solver method, and this is the solution that you get. And if you use these conditions that I have, I mean, this condition for whatever system that you try to do, you'll have the conditions that are applicable for that system. And then to try to solve the equation. So for this one is like with n equation and n unknowns, and then you try to find a solution. So this is the solution that you'd find. But then since you guys have just been exposed to optimization, the question is this the best that you can do? So then now we're like, okay, instead of maybe just writing an equation and solving them, let's write an equation and put in some degrees of freedom and see what is the best that can be done. So then if you try to reformulate that as a optimization problem, and you now give a temperature range instead of like a given temperature maybe for the reactor itself. So now you give a range of temperature and a range of pressures, and you can even give a range of like the flow rates that you want, and even like your hydrogen to CO ratios. So then now the number of equations that you have and the number of unknowns, so now is no longer equal because now there's a range. So a temperature can take on any value. So the optimization is what you're trying to do. You're trying to find what is the minimum point that you get at this temperature. What if you change maybe temperature to 610? What if it's 620? So like those kind of things. And one of the systems that I use the most, I like open source software. So I use like a Python-based optimization modeling object, which is like a Pyomo. Since the problem is like a differential algebraic equation, Pyomo also has like a Pyomo DAE solver package that you can use. So we use the Pyomo DAE solver. And with differential algebraic equations, you need to have some ways of solving or specifying the way you want to solve it. So we use some collocation method. And for optimization, there's a few solvers that you can select. So you can choose whichever solvers you want. You can use your IP-opt, which is based on the interior point optimization algorithm, or your CONOP, which is a different type of solver. So for this one, we decided to use CONOP. Well, the main reason is because CONOP uses like active sets type of calculation, and it was more efficient to use that. And we find that we could actually decrease our impurity from 20.4 in the previous solution to 7.2 at the required ratio that you want. So which means that if you were to take the problems that you had previously and then just write it as a mathematical equation and just to find a solution, it wouldn't be the best solution that you can find, because there's something you can still minimize further to still meet your condition. So this was one of the examples that we came up with. But then, I mean, there's a lot of ways. Let's say, what if we don't want to use the steam methane reformer as it is? What if we want to put in the reformer within a membrane? So the reason maybe you might want to do this is that you might want to produce more hydrogen that you need in the next section, but you can use the hydrogen for other sections as well. So then, but then once you have the membrane, then you need to have some diffusion expression that you can get there. So this is the mass flux that we did there. So this is like the drawing of membrane, and you have diffusion of hydrogen through the membrane. Meanwhile, all the other components don't diffuse through the membrane. So you have the reaction channel in the center, and the diffusion zone, and just the flow of the hydrogen outside. So if we were to set up that, now you have even more differential equations, because you've got the diffusion as described also by differential equation. So now you have a lot of like differential algebraic equation. So, but then you still have to try to simplify it to be able to solve these. So we can ignore like radial concentration gradients and also some other temperature distribution within the system itself. And so here we assume that both layers of stream were preheated to like a high temperature even before we solve it. So then these are the equation that describes the operation of our system. So then we're like, okay, we've described our system. Let's go back again and trying to solve this. But then now this is slightly different. Is you can't just give it to SciPy and use like the Ranskata 45 ODE solver, because now this is like a boundary value problem. So then you use, but then you can still solve it with Python and SciPy ODE solver as a boundary value problem. You just need to specify maybe there's either single shooting method or multiple shooting methods. So then if you try to solve it that way, you get this solution. But then the question is this the best you could do, or can we try to optimize this and get a better solution? And then if you try to set the problem as an optimization problem and have your objective to minimize impurities, the impurities is anything that is not CO and not hydrogen. So you try to minimize your CO2 and try to minimize your water as well. That also comes out. And you could also, you need to have some degrees of freedom. So you have your temperature as a bound and pressures and things that we specified earlier. And now we find a solution that's even better than even the previous one as a steam reformer. So the impurities has been decreased by 6.4% of the previous one. So with this, you can even get a better solution that you've started with just a steam reformer. So this, in a way, is trying to show that for most of the systems, you can write equation that describes the system that you want and solve them. But the big question that you never answer by doing that is that the best solution that you can get? So unless if you can formulate your problem as an optimization problem, you never know that the answer to that question. You just have an answer, but you never know if is there anything better than that you can do. But then if you know that maybe I have flexibility in changing the temperature, I can take it up or take it down and still meet my conditions or still meet the operation of my device. Then you could set it up as an optimization problem and try to solve it. And well, yeah, I just wanted to highlight the platform that I've used. So I like open source systems. So I always encourage people to learn Python programming because Python has been really growing up pretty fast. It has a lot of support. And I mean, it's open source. You can just install it and transfer it the way you want. And now even the national lab, I mean, the government in the United States has like put in some funds to try to devise the optimization solvers that is fully open source that can be used by universities. And they came up with the modeling platform, which is Pyomo, which is Python-based optimization software. Anyone can just install it and run it. You don't need licenses. But even if you wanted to combine it with other solvers that requires license, it does have an interface to those. So Baron is like a commercial solver, and Cplex is also a commercial solver from IBM, and there's a lot of other solvers there. And then some of these solvers are open source, but with Pyomo, you can easily interface it with like your open source solvers and just use it. And yeah, this was what I wanted to share with you and give you just a brief background in terms of how you can apply mathematical programming and the type of problems that you can use. And I believe that mathematical program is growing and is coming to every field now. So I believe like as an engineer, it might be a good idea to give yourself the edge and try learn and develop the skills in terms of optimization now. And apply it. The one other good thing is that now there's also open source software that you can use, and you can teach yourself to apply these. And I think it's useful in a lot of things, as I've tried to to show here. And thank you for your time. I'd be happy to take any question.
Well, thank you very much, Dr. Cornelius. Is there any question that you would like to ask to Dr. Cornelius, guys?
They're in the comments.
Okay.
Okay, sí, hay dos preguntas en el chat.
Yeah, I'll stop sharing so I can see the chat.
Is there two questions in the chat? The first one says, Dr. Cornelius, please could tell us some other linear or non-linear programming applications in other engineering fields?
Oh, okay. I mean, there's quite a lot, especially for linear programming. The key with linear programming is that most of the systems are described by nonlinear programs. But if you have your equations that are nonlinear, you can find ways of linearizing them. Once you can linearize a system, then you can apply linear programming. So in terms of examples, wow, there's quite a lot. I mean, even like your control, most of the controls, even like your automatic controls now, I mean, most of them, they try to linearize the system itself by maybe applying Taylor series to any equations that they have, and then just cut off the higher order terms, and then you just use the Taylor series approximation for whatever system, and that is linear, and then you use linear programming for that. And yeah, in other field, okay, let me see. A lot of researchers are actually trying to find optimal solution. The main problem is that most of the time people tend to do by trial and error. You do something now and then maybe try to change temperature and do something else and try to change another condition. But then if you can formulate your system as an optimization, you can search the whole space just mathematically and know what's the best one, and then only try that in terms of experiment. So even if you are an experimentalist, I would still encourage you to learn mathematical programming, because that will save you a lot of time. Oh, yeah, I see in the chat there's also in terms of biomedical field. Yes, and even here at Purdue University, I know there's Professor Clarice, who works a lot in terms of biomedical field. What he's looking at is in terms of production, let's say, of medicines, whatever tablets. So the process that is used for that, or like batch scheduling, in terms of scheduling of your batch processes as to when you're doing this and what comes after that. That's like a planning and scheduling problem. So then he sets that up as an optimization problem, and then try to solve that to find the best way. And one other thing with scheduling is sometimes you have changeovers. You don't know what you should do first. Like if you have a process that can happen in like one unit, should you do process A or process B? So trying to decide between that. You set up your system as an optimization, see if A, how long does that take? See B, how long does that take? Which one is the most optimal of the two? So that's like an optimization problem that people are looking at. And what kind of books can we read in order to acquire more knowledge about algorithms, linear and yeah, this one is a good one. So I would say for like the open source software, the Pyomo that I've been talking about, they actually do have like a book that has been published. So it's published by the people at the Sandia National Lab. So there is a Pyomo book. So I would say use that book. It has a lot of examples that you can try play around with. The one of the best way to learn optimization is to start by describing simpler problems. And they actually do have simpler problems that you can try, describe, and then solve those. So I'd say get the Pyomo book and try the examples that they have there. Okay, let's see. Yeah, getting more questions. All the nonlinear can be changed to become linear, or only some of them? Oh, so this is a good question. So if you have a nonlinear system and you want to find a linear approximation, the one thing that you should know about that is that that is only an approximation, and the approximation, the linear approximation of a nonlinear system is accurate around the point of the approximation. If you go far from the point of approximation, then you lose your accuracy there. So then you need to balance between your accuracy of the model and the simplicity of solving it. So that's why we don't just solve everything as a linear program, because once you try to linearize everything and you are too far from the point where you linearize, then your solution is inaccurate. So then that's why you somehow you are forced to solve nonlinear programs, because you want to have a much more accurate solution to what you're trying to do. I hope solved that. Oh, and is there any platform where we can find research of chemistry? Well, yes, the main challenge with chemistry is that most of the equations that people are trying to work with in chemistry, they are highly nonlinear and highly non-convex. But the methods to solve nonlinear programs are getting better and better. So for now, I mean, the systems that I work with, I describe the reaction kinetics, and that's usually nonlinear. But that's usually the most part that is mainly nonlinear. So I still try to find a solution to that. So yes, chemistry, yes. The main challenge at the moment is that most of the algorithms still take a long time to find a solution. But that's an opportunity for algorithmic development. For me, I think most areas that even maybe algorithmic solutions are still slow, those are actually good areas to work in, because if you are looking at algorithmic development, then that's huge opportunity. But if you're only looking at applications, you can still try to simplify your expression to get the best answer that you can get. But even though it might not be as accurate as you'd like it to be, but then you need to pay attention to that once you simplify the equations that you have, then you lose in terms of the accuracy. That's one thing you need to keep in mind. Okay, all nonlinear. Okay. Can you use linear programming in the field of molecular? Oh, well, it looks like a lot of the question are asking if you can apply linear programming in a lot of fields. So, okay, let me try to answer it this way. For simplicity, you actually can, but you need to pay attention that once you try to linearize equations, you lose accuracy. So then the solution that you get might not be as accurate, of which I think that's where the key is. So then that's why you need to pay attention to how you linearize the equation that you get to produce your linear program and solve everything as a linear program. So linear programming is very useful, especially if you can describe your system with linear equations, or if you can simplify your equations to be linear, but still relatively accurate. So that could be done. And most of the fields, most of the equations that you have are nonlinear. So at some point, you will have to at least learn nonlinear programming to get the much more accurate solution. Let's see. In your field of expertise, interpreting phenomena from perspective model. Oh, I mean, in most fields, you do have some fundamental work that you do on trying to find theories that apply to that field. That's not necessarily optimization, that's not. The optimization comes in when you're trying to find the best point among various points, or the best operation something, or you try to find a best way amongst a lot of given ways. So that is optimization. So yeah, I think you needed to clarify that in field of expertise, the fundamental search of the knowledge and the concepts, that's not optimization. That's like the conceptual development. That's different from an optimization search. Oh, I'm happy to have received a lot of questions, but yeah, this is good. But yes, in terms of linear programming, I'd say it would be a nice thing to learn. Everyone, they are very efficient solvers out there that works. So try to at least maybe even find some open courses online to learn a little bit of linear programming, and try simple linear programs that you can formulate and try to solve those. I think that'd be a good thing.
Is there any other question, guys? Bien. Dr. Cornelius, I think they are all the questions we have.
Oh, yeah, thank you very much for the invitation. This was nice, and I was happy to have a chance to talk to undergraduate students here. And oh yes, if you have any question, yeah, I could put my email on the chat. Well, and for those that are considering grad school or things like that are finishing, so feel free to have a look at our programs and apply to Purdue. Well, that's one thing.
Thank you, Dr. Cornelius. I'm just going to read this acknowledgement that from the University of Celaya. It's in Spanish, but I can translate it.
Yes.
Faculty of Engineering of the University of Celaya grants the following acknowledgement to Dr. Cornelius Masaku for his presentation with the topics Mathematical Programming for Systems Engineering, Design and Optimizations. Dr. Cornelius, it was a pleasure to have you with us. We hope we can invite you in the future and have future interactions with you. So
yeah, I hope so too. I hope so too. Thank you very much. I highly appreciate this. Thanks.
We appreciate it. Thank you. Gracias a todos por su asistencia a esta conferencia. Les recordamos que tenemos a las